Right, okay, special relativity. As I said, it is a little bit difficult to get your head around, first of all, but just bear in mind that there are basically two equations in this that you need to know and you need to be able to put numbers into to get your marks. Obviously, ideally, we'd like you to understand it as well, but don't panic too much if you're thinking, whoa, okay, everybody thinks that in this first time round. Okay, so those are the two equations. You saw them on that video that I made you watch on Friday. Time dilation and length contraction. So that's how you work out how the time differs, depending on whether you're traveling very, very quickly or stationary. And same with how the length differs. Okay. So what is special relativity? Okay, so it's all down to Einstein and talking about how light moves and how matter moves because of light. And I showed you a video a couple of lessons back about the Michelson-Morley experiment. I mean, he said he did this experiment where he shone light, and they thought at the time that light went through something called an ether, like a material called ether, just like sound travels through air, light travels through ether. And they said that if light travelled along with the same direction as ether, it probably would travel faster than if it travelled in an opposite direction or at right angles to the ether. But he proved that that wasn't true. Okay, so he proved that light travelled the same speed no matter what. Okay. So something that's really important when we talk about special relativity is these frames of reference. Okay. So frames of reference is just like if you're on a train, you're technically moving very, very fast on the train, but to you feel like you're stationary. Okay. But if somebody was observing from outside the train, they would see you whizzing past on the train, so you'd be moving very quickly. Okay, so similar kind of thing. This example here is we've got an old school train here, and this is moving at a constant speed of 60 miles per hour. So you get it from your seat and you go to buffet car, which is located towards the front of the train. So you're going forwards on the train. So you're walking at a speed of 2 miles per hour along the train corridor. Okay, so to you think you're just moving at 2 miles an hour. Okay, you're just moving forward 2 miles an hour. Okay, because that's how you perceive it. That's your frame of reference. So your speed relative to the train. So if you look down at the floor, the speed that you are traveling at is 2 miles per hour. Okay. So relative to the train, you're just moving at 2 miles an hour. You're moving 2 miles an hour faster than the train, really. If you carried on walking at 2 miles an hour, you'd end up walking off the edge of the front of the train, wouldn't you? Your speed relative to the ground, however, is if you could look through the train and see the ground whizzing past, what do we think it's going to be? 62, yeah. So you're traveling at the speed of the train plus that 2 miles per hour. So you see what I mean? Like, you're still traveling at the same speed, but depending on what you're referring to, your reference frame, you're traveling at a different speed. Right, your speed relative to a cyclist traveling anti-parallel to the train at 10 miles per hour. So basically that means you've got a cyclist and he's traveling anti-parallel, so that means the opposite direction to the train, at 10 miles per hour. So your speed relative to a cyclist traveling anti-parallel to the train, now we usually get two answers for this one. What do you think it is? Ah, okay, this is interesting. This usually happens. Okay, so hands up if you think it's 52. Or people have changed their minds. Hands up if you think it's 72. It's kind of 50-50. It is 72, because if you think about it, if something goes past the opposite direction, it seems like it's whooshing even faster. Yeah, so it is 72. If you were traveling by the train, so if the train was going like that, and you were like, it would feel like the train was going slightly slower than it actually is if you were traveling in the same direction. But because it's traveling in the opposite direction, it's pushing past you faster. Yes. Yeah. See, sorry. because you're basically moving in that direction, it's moving in that direction. So you're basically adding up the distance traveled. So the train's going in that direction, you're going in that direction, okay? So if you were just stationary, the train would be going at 60 miles every hour, okay? But because you're going in that direction, you're moving some miles per hour that direction, and the train's moving some miles per hour in that direction. So the amount of miles per hour that's different is bigger. Does that make sense? Sorry? If they're moving together, well, the cyclist is kind of keeping up a little bit with it. So if you were standing still, it would be going at 60 miles per hour. But because the cyclist is kind of keeping up with it, it seems like it's going slower than it actually is. Okay. I did tell you it is quite difficult to get your head around. Okay, so it's kind of like, I think it's something you've got to keep thinking about, and it is really tricky. I remember the first time I did this, I was like, no, I don't agree with that. But that's how it works. Okay. So have a think about it. If you're ever on a train or if you're on a bus and something goes past you, okay, does it look like it's going faster or slower, depending on which direction it's going in? Okay. Right, and great. Things become more complicated when you consider the ground outside is not at rest. It's rotating very quickly around the centre of the Earth's moving very quickly around the sun's moving very quickly around the galaxy, which is also moving around space. Okay, so we tend to, in physics, we just sort of say, oh, the ground's our reference frame usually. Okay, but so this example highlights a subtle but important problem in physics. In order to fully define how an object is moving, it has to be given a frame of reference. So we usually just give it a frame of reference. And up until now, we've just been saying, oh, it's normally just the ground. Okay, the ground is still. We're assuming it is. So the laws of motion worked out by Galileo and Newton, which is what we've used so far, depended on the assumption that absolute motion exists, i.e. motion with reference to something at rest. However, everything we know of in the universe is in motion. So, can we find absolute rest against which to measure absolute motion? Don't know. I mean, there might be something, the very sort of centre of everything, but we don't really know. So, next page we talked about already, so that Nicholson-Morley experiment. So we can skip past that. And then we'll look at special relativity. So, Einstein is the guy that put all this in motion. So Einstein he did a lot of thought experiments. He thought a lot. Okay. So he had two postulates, and these are really important when we talk about special relativity. Okay. And two, I guess, definitions. These aren't your postulates. Postulates are bold ones here. That's just definitions, sort of scientific definitions. So paradigm is a typical example of pattern of something, a pattern or model, and a paradigm shift is a fundamental change in that. So basically, Einstein brought about this paradigm shift. Okay, so a lot of work have been done developing theories of this luminiferous ether, and it took someone from outside of the established order to see things a different way and see a way forward with the problem of light. Okay. So Einstein's theory is very simple. So it all boils down to these two postulates. The laws of physics must be the same for all observers, no matter their frame of reference or the reference frame. So that's one. So laws of physics don't change. And the second thing that doesn't change is the speed of light. It's constant for all observers, no matter their frame of reference. And it's because that speed of light is constant that other things have to change. Okay, so we talked about that time dilation, the length contraction. Something has to give. Because we know the laws of physics don't change. So distance is speed times time. Doesn't matter where you are. But if the speed stays the same, then the distance and time tend to have to change to fit in with that, the law, the postulate. So the first of these two postulates is easily agreed upon. If it was not true, We would need to apply different laws of nature to different systems based solely on what they were doing at the time. For example, to calculate the speed of someone, you measure the distance and the time taken to cover that distance and divide the first by the second. You would not need to do anything different if the person walks on a moving train or if they walk past the station platform. The same method is used and the same relationship applied, though observers may disagree about an absolute speed of the person if they switch from one frame of reference to the other. But you still use distance is speed times time. That equation still is true. The second, the speed of light is constant, is this paradigm shift, okay? So we're just saying that it does not change on how you view the universe and everything in it. There's a huge wealth of experimental evidence that this is true. However, many physicists were initially unwilling to make the break from their disproved theories.